two caveats. One is that um, that community forum went longer than expected, so we'll have a slightly shorter roundtable. And also, we're gonna dedicate the time mostly to presentation by Carlos and Nick, so it won't be terribly round. Though, with that being said, even if Wukash and I were to present, it still wouldn't be round in any technical sense. But um, uh, Carlos and Nick, yeah, please go right ahead. As I understand it, you had like a Packlet design review yesterday.
That's
I'm
right.
not sure how much you mm, I'm not sure how much discussion there was of the actual research that you're doing.
Fair
So
amount, actually.
presumably,
Fair
oh,
amount.
okay,
Yeah,
good.
yeah, actually, surprising amount in the end. I think
Yeah.
Stephen ran over two meetings to stay for the discussion.
Oh, yeah, that happened.
So,
Yeah.
yeah, anyway. Yes, so one of the. I mean, maybe I can just share this for the time being to have something in front of us. Oops. Oops, oops, oops.
Hyper network theory.
Give me a sec. I had to reshare. I mean, that's just a fancy name to say hypergraph without labels.
Is this kind of are you kind of workshopping this term in preparation for that conference in July, or just in
um,
general do you like the term?
I haven't seen the term used that much, but it's so natural because people call it higher order network theory. It's much longer,
Mhm.
um, and I guess it is a bit sort of quote unquote political in the sense that in the higher order in the higher order community there are feuds of simplicial complexes, hypergraphs, multi-layered networks, all these kinds of things.
Mhm.
I've had conversations with people who thought that hypergraphs and simplicial complexes were actually separate, distinct approaches, which is quite shocking. Um, so yeah, I mean, when I told them no, but a simplicial complex is a special case of a hypergraph with more structure. Um, they said, "Are you sure about that?" And these were people working in the community. So there's some um, politics, scientific communication politics involved in calling something hyper network theory. Um, but I think the name is completely earned by the discipline because what you're doing is literally extending network theory to hypergraphs. So if you call network theory what you do with graphs, what you do with hypergraphs is hyper network theory, right? I mean, there's no, almost no escape
I see.
in the name.
So if just as I understand it, you're trying to avoid the language that's being used today, since it's so divisive, and introduce a term that can accommodate several of these approaches without invoking the language that's currently divisive. Is that
Not really,
part of it?
not really. So because in some sense this is more divisive than it should be, in a way. Because some people would call it higher order networks, right? And that is not divisive,
Yeah.
but that could mean many things. But I'm trying to be more specific. I'm trying to be quite concrete and say
Mm.
I am doing network theory with hypergraphs, right?
I see.
So
I see.
so that's why
Okay.
hyper network, right? So it's not being diplomatic. Like it's not particularly yeah, trying to be more neutral or more in between. It's quite trying to be partisan towards hypergraphs, but at least you're being upfront about it, right? So I don't say higher order networks and then all you see is multi-layer
I
networks,
see.
right?
I see. Okay. Okay.
Anyway, so a brief recap for the viewers. Something we know and we're very familiar with in network theory, in standard network theory, is what we call adjacency rewriting, right? Or we here at the Institute call adjacency rewriting, which most people know as just paths on graphs or simply following or computing distances between edges, between vertices, sorry, on a graph. So the minimal example here being, if I have this rewrite rule, obviously, so actually I'll show you first the adjacency matrix case. So if I have this graph, it's adjacency matrix, so this is the test graph. So the adjacency matrix of test graph, which is just our general hypermatrix function, gives, sure enough, it gives a sparse array with 3 entries, 1, 2, 2, 3, 3, 4, as it should, because it's just a chain of three edges. And then the idea is, because you want to, so actually maybe I could just do this with the drawing. Graph draw. So because you want to, so let me illustrate this, right? So by the way, Nick, the next step would be to input labels as well with this editor. That'll be pretty cool.
Yeah, if you have an idea for the how you do it, the simple way is just to provide some simple input that you can put any option that you can put to the hypergraph, like vertex label, arrows, and then just do whatever.
Yeah,
you can do that.
Right. I agree, but I think it might be quite easy to maybe one idea.
But
I don't know how.
labels-
Yeah, go on.
Yeah, for labels, maybe, yeah. Similar that you have like vertex over there that you can rename. Maybe just something similar to also put a label.
Yeah, I would say yeah. You like click on an edge. Can you actually select edges in this current version?
Well, in a way, yeah, because you can drag them and cover them,
Right.
so you can select them. And it shows the last edge you selected over there. You can't do anything with it, but it shows you the last edge.
Right. Yeah, because I think that'll be the natural thing, that once you have, like, now the vertex is selected, right?
Yeah.
So I can rename.
Well, you can. It's just not showing you like the cursor, but you can edit the tree there actually.
How do I vertex mode maybe?
No, it's not showing that you can edit it. It's like at some kind of bug. I don't know how to fix, but you can like right there and backspace it. But the cursor is not showing there for some reason. I have no idea.
But does it actually rewrite?
Yeah, if you rename it, it will rename it. Oh, now it's free again. So you have to select first.
Select.
Yeah.
S. Rename. Okay, that works. Yeah. So exactly this behavior, I think, for edges is just fine. But the problem
Like,
is, I would use this vertex functionality to be vertex labels and the edge to be edge labels, right? Or maybe after our discussion, maybe we had to, I mean, depending on what Steven thinks and how we decide in the end, we might want to do everything on edges, right? And forget about vertices.
Oh, I'm not sure about like free vertices are still pretty good. Yeah.
I agree. I don't have a strong opinion on it, because, to be honest, they are equivalent in some sense. But if
There's no reason to remove this functionality if it works. They can, they can coexist together.
I agree. I think it was just a question of, we presented it, and we made the emphasis, and they thought the emphasis was the kind of the functional important part, and it wasn't, right? Because the function is very general, and then we can build on top of that function something that is particular, something like is more like diagram, or more like just networks, or more like, right?
Yeah.
Okay, sure. So anyway, what I wanted to show you here is, is that if I get this situation where, if I get this situation, I'm in edge mode, and I want to go from here to here, and then I want to go from here to here, what you would do is you take the adjacency matrix and you contract the index that is shared, right? So here, I mean, it's very dark, unfortunately. So
You mean the labels?
yeah, the labels.
Yeah, I can't see them.
Yeah, it's very bad. So
Well, I think you can put options to the hypergraph draw, right? As initial options, like label style, for example. You can,
in
In the
the
input cell.
hypergraph draw, When you're just initializing the whole widget, you can.
Oh, really? Oh,
some
nice.
of you.
So if I
Yeah.
put the option here,
Yeah,
oh,
because
interesting.
you can put the whole hypergraph as your initial starting point, right?
Right.
And it inherits all the options. Okay, right now I think.
Ooh.
Well, that's the labels, not the style. You need label style.
Vertex label style.
Yeah. Now it's just all your labels are literally white.
Yeah, literally.
The color. Label, not
Label.
labels.
Okay, so fantastic.
Couldn't you just make that something to adjust within the editor itself?
Oh, sure.
Sure. I mean,
But it will occupy more space, and you have to like think beforehand what you actually want to put in there.
that's so nice.
Aha, that's better.
Okay, so yeah, so normally you want to say something like, I'm walking from 1 to 2, and then from
Yes.
3 to 3, and the idea is you have your indices in your adjacency matrix correspond to that situation, and when you multiply, you're basically finding moving to from 1 to 3, right? So that's what this formula is doing here, right? I'm taking the adjacency matrix A, and I'm using index contract. I could just use matrix multiplication, just A dot A. But I want to be very explicit about the indices, right? So I want to say I, P. So P is 2 basically here. I mean, I guess I could just show it. P. And I guess I could show the same thing for here, just for the sake of I and J.
Mm-hmm.
So that's exactly the situation that I wanted to show, right? You have A on the edges, and then A squared on the A on the yellow edges and A squared on the orange edge, right? So sure enough, if your initial graph is this one, right, and you compute the square of the adjacency matrix, what that square is computing is, if you understand the meaning of doing matrix multiplication in this context of graphs, is saying choose any 2 vertices, and it's gonna, because these are simple and we're just doing simple for now, it's gonna determine whether there is a path of length 2 between any 2 given vertices, right?
Mm-hmm.
So in this chain of 1, 2, 3, 4, clearly there's a path of length 2 between 1, 3 and 1 between 2, 4. So that's why when you multiply matrices, you get this, right?
Ding ding.
Get 1, 3, get 2, 4. Now, that's the well understood story that everyone learns about when they do network theory. Now, how do we understand it in rewrite? In rewrite terms, we take this, calling back to our origins in the institute, this sub-axiomatic sort of approach or more machine level type approach, where instead of grouping the information of your graph in an object that is algebraically amenable, that is ready to be manipulated algebraically and sits on some nice monoid, has like associativity and all these nice properties, instead of that you say, well, I have a graph, I have computational procedures in a graph, which are technically in our context rewrites, and I'm just going to apply it to that, right? So the rewrite is the obvious one, because it's the rewrite is somehow expressing the question that we were asking the graph. We were asking how many paths, or is there a path of length 2 between these 2 vertices, and we transform that question into something that is just a rewrite. So literally you find the length 2 path between 1, 2, and 3 vertices, and then you rewrite the path that exists, and basically make a graph into another graph with this rule, right? So because the new graph, so if you apply this to your graph, you're going to get, from a graph you get another graph, you get another graph, you get another graph. All these graphs are going to have an adjacency matrix, right? So the question is as follows. If I have my graph, this one, G, I take its adjacency matrix A that I found here below, which is obviously this sparse array, very clearly here. If I take A squared, what graph how do I construct that graph from the original graph just by doing rewrites? That's the question, right? It's a little exercise. And the solution to that exercise is this function, basically, this thing that I called one-pass rewriting, which basically means that you take all the possible hits of your rewrite rule and you apply them independently, simultaneously. Instead of the usual multi-way or sort of rewrite system type application, which you can be dependent on overlaps and keep track of causality. Instead of that, you look at your initial state and you apply the rule in all possible matches, and then you basically delete everything else and you just keep the hypergraph that results from those. So basically you're adding sort of you scan all your graph with an empty graph with the same vertices, and you're basically storing all the new edges that are being created in this new graph, right? So I call it the one pass because you basically do a sort of a one pass on the entire state of all the possible hits of your rule, and you basically add them together in an empty graph on the same vertices, right? So sure enough, after that procedure, we get this graph, which is indeed the graph that we got by doing a squared. So here, this function here, hypermatrix graph, is basically drawing a graph or drawing a hypergraph from a hypermatrix, right? So that shows the sort of classical situation in hypernetwork theory. Sorry, in network theory of the correspondence between matrices and rewrites. Now, what would be interesting is to generalize this to other networks that are not necessarily pairwise. So in particular, something like three graphs. So we have a very simple rewrite system here, where we're just taking three triangles in this configuration and we just rewrite them together. Easy way to imagine this is a tetrahedron without one of the faces, and you're basically rewriting the face that's missing, right? So as an example, you have this state, which is basically just two of these objects, and because you match in two possible locations, you get two possible hits, and the application of the rule gives you two possible hits. So if we do the one pass rewriting, which is just the same function, this function is general for any rule, right? Sorry, here. Up here. This one pass, it just takes a rule and a hypergraph. It doesn't really care about anything else. If you apply it to this one, naturally you get this hypergraph as a result, right? Because in the first hit you just get the left triangle, and in the second hit you get the right triangle, and that's the result. So the puzzle here is how we reconstruct, how can we find this hypergraph from an algebraic operation on matrices, right? So first thing we do is we extract the adjacency matrix of this thing. In this case, this is a 3 matrix. So sure enough, no, it's here. So okay, so there's several of them because this is capturing all these 6, right? So there should be 6 elements, as it says. And so the question now is, what is the product that we should define? So the product is something that, if viewers joined our workshop a couple of weeks ago, is the so-called Bhattacharya-Messner product. So it's this contraction, right? So this formula here, what it's saying is, this is a very unfortunate. This was the live coding question I had for Nick, because obviously this index contract is contracting everything because it's repeated, right? So the goal here, as you might remember, Nick, is that we want to only contract P.
Well, we have to rename them, unfortunately, like unique indices.
I see. So let's do A,
And B.
C, and let's do
X.
Y, Z,
Yeah.
for example. So do you think this will work?
Should be. It's that Einstein summation version there, right?
That's the one that you told me, yes.
It's not the built-in symbol, so yeah.
Yeah. No, this index contract is defined with a summation.
Yeah.
Yeah. This is the right one, right? With the.
Sure. Yeah.
Okay. So. Okay. Yeah. That's easier than I expected, of course. But then, what we want to do is basically apply literally the same thing to the result and see if the magic happens. So I missed this. Wait. It's here.
That's a bit weird because the key says that you have a binary edge.
Yeah, no, I have to update this. So
this is like a 6 order, right? Because you have a rank 6 tensor be there.
rank 6. Oh yeah, because there are 6 vertices, yes. No, there are 7 vertices.
No, there's 7 vertices, but because you contracted. That's basically how you contract it, right?
Oh.
So it's not that simple.
But that's right. Of course, in the contraction, it forgets about the middle vertex. Well, wait. But that wasn't an issue here. Here we also contracted and we.
Well, that's just a coincidence. You don't expect it would continue to all orders, right?
No, for sure not. Yeah, this was the real issue. I remember now. Yes. So basically, you need. Yeah. So matrix operations forget about indices, right? Because if they are contracted, they are basically gone.
Well, because you're contracted. Yeah.
Yeah. Exactly.
And Einstein's summation tries to show it very explicitly. So what you're left with is those six indices: ij, ac, and yz.
Right. That's the problem. Of course. Sorry. Yes, that's the problem. The problem is that those indices should be somehow renamed to just ijk. Like I equals a equals I. Yeah. I equals a, j equals y, c equals z. Right. So you come down to a 3 matrix.
But how do you do it operationally on a matrix? That renaming.
I don't know, because in matrix algebra, mathematically, you don't have this issue because you just don't sum over the repeated indices. It's a problem with the fact that
giving them the name not gonna reduce the rank of the tensor. It's still gonna be 6 rank, right? You can pretend they have this indices that you want, but what do you actually do with the tensor?
But the problem is that the operation is in some sense technically different if you give it different names. Because
what is the operation?
Because the operation is like the indices are repeated. It's not that they are the same but just copied 2 times and they can have 2 different names like a dummy variable name. They're actually repeated, meaning that when they occur exactly with the same value, right?
Well, like broadcasted, you mean, right? I think. Well, you actually can try it because the Einstein summation have this notation. You can use arrow, and then put what kind of indices you want on your output tensor, and see what happens. But like actually, give it the same name that you had previously,
okay,
with only ij's.
Sure.
Right? But then, and I'm not sure whether it would work, but let's see. But then you just say arrow. So
where arrow where?
Within the string. I think the notation works, but I'm not sure. like arrow and say what you want as an output, what kind of indices.
RJK.
So yeah, let's see.
Does that work? This arrow here?
I think
Let's see.
I don't remember, but I think it does. Yeah,
Okay.
whatever it did, maybe that's exactly what you want.
Okay, that's interesting.
Yeah,
Because
I
now,
remember doing it. I remember coding it. That was the initial problem, that Einstein's summation kind of was not general enough, and I made it to work like this way, but I don't remember how. It's some kind of broadcasting of indices so that it actually produces whatever indices you want. It kind of made sense. It's almost the only possibility you can code it. It's like there wasn't really any room.
yeah, no, but
There's no ambiguity.
that's right.
So probably it's the right behavior.
I mean that looks. I mean, I'll have to reverse engineer the shape of the hypermatrix again, but without doing that, I can already see that this is correct, because 1, 2, 4, 2, 5, 7, right?
Hmm.
Yeah.
So we don't have to waste time just reverse engineering that, because that's, at some point we'll make decent way to extract things systematically. But anyway, okay, so actually that's great, because we were not able, for anyone watching, we were not able to do this before. So this is the first time. This is the first time that I can actually show a non-graph rewrite algebra correspondence. This is cool. This is cool.
Yeah.
So
You
yeah,
can make an actual hypergraph. Why not? It shouldn't be that easy. I think that should work. The key is not even treated in any way.
okay. So
But that should work. Like just replace B with B3 and see whether and
But
remake your hypergraph.
surely I have to change this, right?
I'm not sure whether you can even ignore it. Just put 3 in there and remove the cycles. It doesn't matter. Put like an empty list as a second argument. Like it would make it directed, I think. But who cares? Let's just make a directed one.
Sorry,
After just type 3, empty list.
like this.
Yeah, that means directed symmetry. Ordered. Yeah, so they have arrows. So good enough.
That's actually perfect. And wait, how would the because this doesn't make it hypergraph. I can just make it undirected here.
Yeah, you can override the symmetry here. Let's say unordered.
Yep. Okay. Good. Yep. That works. Anyway, so yes, so that's the lesson learned, that we're very close, because now we are actually polishing the details of how these things are working. So we're very close to having the actual sort of suite of functions that you can use to just run these higher order searches and because remember, I mean, maybe to wrap things and bring people, bring it home, so to speak. This was a long detour to investigate complexity of hypergraphs, in particular because we realized, which as many people do, many people agree on, that the most natural path into hypergraph complexity was spectral theory of hypergraphs. And we checked the literature, we checked the standard reference on hypergraph, on spectral theory, or so-called spectral hypernetwork theory, or whatever. And that main reference basically took hypergraphs, reduced them down to graphs, and then used spectral theory on graphs, right? So just plain ordinary graph spectral theory. So this, to me, was this thing that we just able to, so this reality check that this works, to me was the requirement to have a functioning higher order approach to spectral theory, right? Because you basically, I mean, my belief, I'm kind of 95% confident of where I'm going to say right now, but my suspicion, my very strong suspicion, is that for each such rule, so for this rule, you have graph spectra, right? The usual graph spectra based on matrices in linear algebra, like everyone knows. My suspicion is that if you change your operation, if you change effectively your rewrite rule, which in some sense is the adjacency condition, right? Like you're matching a motif and you're checking adjacency in a different way. You're checking different topology with different conditions. My guess is that this leads to a different spectral theory, because it's a different algebra. What the eigen problem here means is completely different, right? It's not even so. An interesting question is how much one depends on the other, how much you can reconstruct one from the other, because obviously you could always define, instead of rewriting just a V into a line like this, you could always rewrite a zigzag into a single line, right? That spectral theory is going to be very closely related to this theory, because it's kind of a Sesky adjacency, right? It's like 1.5 data rewritten to a single edge. This is two pieces of data rewritten to a single edge. If you have a chain of 4 edges and you rewrite it to a single edge, that's going to be kind of the square. It's like taking squares, right? It's like you instead of operating the adjacency matrix, you operate the adjacency squared, so you get the 4th power when you do that, right? When you take the actual product, you get the 4th power. So some of these rewrites are very obviously related to one another, right? Like you can just explicitly see these relations in very special cases. So the general question is, how do they relate in general, right? Like this is there any relation between the spectral theory that comes from this ternary Bhattacharya-Messner product with ordinary spectral theory of matrices? Who knows? My guess is probably, because Edina Gang, for example, has these papers on the question of generalized groups and so on, and it does seem that there is a clear analogy, especially if you put yourself in the right context, which is non-commutative rings, for example, right? So those questions, I think, are quite interesting, and they are in a way, for people who's followed the Institute from the very beginning, in a way these questions are very tractable and concrete versions of the questions that we were posing at some point of how do these two different formal systems relate to each other, and how do these theories compare and so on, because at the end of the day each of these patterns spans a different sort of rewrite theory, and so which entails a different spectral theory, and each of these is kind of its own world. So having such a unified perspective to compare them, where they are literally both just rewriting the same kind of object, and you can study how they interact, how they grow, their complexity, their all these natural questions in the context of graphs and rewriting. Well, it gives you much more sort of a point of entry than before, which was some kind of philosophical question of how do you relate these things and so on.
Oh yeah.
So it's very nice. It's very nice.
Well, that was very well summarized, and boy, it's exciting to see, initial cases of these things that we wanted to do live. We had one last week. Now we have this one. I don't know what else to say.
It's great. It's great.
Yeah, it's springtime in the hyper world.
Yeah, it's definitely the productive season.
Yeah. Well, oh gosh. Well, we've gone a little over time, and I have another meeting I have to get to.
Sure.
But
any comments, Nick, that you wanted to add?
Yeah, Nick, you want to close the discussion?
Well, personally, no, but there's some comments to you personally, James. So
Oh,
listen.
to me? But Carlos has been speaking for the last. Okay, hold on. I actually don't have the YouTube link up. Would you mind reading that?
There's a guy called Adam Miller said that you
Oh, hey, Adam.
Yeah.
What did he say? What did Adam say?
Where? Wait,
I guess
where?
it's not a question, but it's a Twitch. It's on Twitch.
On Twitch.
Yeah. I guess it's not a question, it's just some kind of comment.
You want me to read it?
He wants to chat with you. Yeah, it's like, I'm afraid I cannot stay for the remainder of presentation. By the way, my name is... I spoke with James a few weeks ago. Please let me know if we can chat again. Thank you for answering all my questions. I'll be back next week.
Thanks, Adam. Well, not to give away private details online, but Adam, I do have a meeting on the calendar for tomorrow at 5 o'clock Eastern. So presumably, Łukasz and I can meet with you then. So if you can't meet then, let me know. But otherwise, it's been my presumption that we'll be meeting then. And yeah, I owe you some responses to those emails that you sent me. Thanks for publicly shaming me. That's always a good way to incentivize a faster response. So anyway, but that's a kind of a distraction from what was a very nice presentation on Carlos's part.
No, this is the point.
In the coming weeks, we might have some more live streams specifically oriented towards this. Carlos will be giving a talk to what I believe is a network theory audience in July, and so we might I don't know what to call it. We might have some kind of teaser lectures kind of before then, maybe oriented towards different audiences, or maybe including some content or ways of address that Carlos wouldn't include in the actual talk, but he might include here. So yeah, this is coming along well, and I think within the next few weeks you can expect maybe some special events on this topic.
Right.
And I know that Carlos is discussing. Can I say that there are some discussions with some of the participants from the workshop, and the audience can maybe expect some follow up in that regard. So
Sure.
it's not determined yet, right?
Yeah. No concrete details, but that's clear that in the coming weeks we'll be leading up to NetSci, which is the conference where I'll be presenting the stuff. So yeah, it'll be the real test. I mean, all these things are very neat, but it will be the real test when the community, the higher order community, gets its eyes on the actual functions and the theory behind it, and it'll be exciting to see what people in this network theory community has to say. It'll be fun.
Yeah. All right, everyone. Well, thanks, guys, and thank you to those watching, and we'll see you next week. Cheers.
All right. See you, everyone.
Bye-bye.